Thank you so much. So my name is Bonnie. I'm a research engineer at Google DeepMind, and today I'm excited to talk about towards world models and general agents. So the vision we have at DeepMind is we want to build general agents that can do anything humans can do on a computer, in the world, and how we've been approaching it is through simulation. So over the past few years, we're seeing a path towards increasingly general agents. So let's go back to the beginning of DeepMind. In 2013, we released the breakthrough DQN paper called Human-Level Control Through Deep Reinforcement Learning, where we saw for the first time deep RL approaching human-level performance. But it was human-level performance in these single Atari games. Then a few years ago, the research focus expanded towards more complex real-world interactions, like the work on human timescale adaptation in open-ended task space, where we generated millions of environments and trained agents to adapt on human timescale to these new environments. So at this point, we were wondering how we can scale further to more environments and how this generalized to the real world. So last year, we introduced Genie 2, a large-scale foundation world model. This was a transformative step, as it enables generation of an endless variety of interactive 3D worlds. This capability provides an infinite training ground for open-ended learning. And it's a fundamental shift from learning in environments to learning from and generating environments. And it's critical for scaling AI beyond human datasets and fostering self-improvement. So Genie 2 is the first foundation world model. So everything you see here is entirely AI generated from a single prompt. Genie 2 generates interactive 3D worlds. You can interact with it with the keyboard and mouse actions shown in the bottom right. So everything here is generated frame by frame. World models is a foundational AI system that learns the underlying dynamics of how the world works. A key capability of Genie 2 is generating an endless variety of interactive 3D environments. So this means that the system is not limited to a fixed set of training grounds. It can generate novel environments on demand, prompted by a single prompt, image, or even a sketch. And we can use these environments to train and evaluate embodied agents. It would also be really fun to play with, unlocking a new form of human entertainment. So what are world models? World models are AI systems that learns the underlying dynamics of how the world works. Like humans, we have an abstraction of how the world works, and we can predict what the future would roughly look like. World models are like neural network simulators. The world model architecture in earlier version Genie 1 aims to learn a compressed predictive representation of the environment directly from visual data. So both the video tokens, so we have a video tokenizer that tokenizes the frames into discrete tokens, and then we have a latent action model that infers the action between each frame. And then both the video tokens and latent actions are fed into the dynamics model, which predicts the subsequent frames iteratively. So this enables the model to imagine the future, effectively rolling out its understanding of the world. The dynamics model is implemented as a decoder-only mask GIT, and the video tokenizer uses a VQ-VAE. And we saw some nice scaling laws by scaling up this model. We see the training law scales log linearly with respect to the amount of compute and also the model size. And so here are some examples from Genie 1. So this was really a proof of concept. This only focuses on 2D platform videos, and the video model context only lasts for a couple seconds. So it was really a proof of concept, and we wanted to scale this up with Genie 2. So with Genie 2, we leveraged state-of-the-art architectures by using a latent diffusion model, enabling highly detailed and controllable world generation. So the generation process starts with any starting frame. This can be AI generated, this can be real-world images, or synthetically generated. It may exist in the real world. So then this image is encoded into a latent representation. And then the Genie dynamics model takes in both this latent and the current action being taken, that's the keyboard and mouse actions, and generates the next latent. And we do this auto-regressively at each step, taking in previous latent and the current actions, and generates the next latent with a large transformer dynamics model. And each of the latent is decoded using a diffusion model into the frames. And at inference time, Genie 2 can be sampled auto-regressively, taking individual actions and past latent frames on a frame-by-frame basis. And we also use classifier-free guidance to improve action controllability. So let's see some results. So we see that Genie 2 shows fine-grained action controls. It responds intelligently to action taken by pressing keys on a keyboard, identifying the characters, and moving it correctly. So for example, our model has to figure out that the arrow keys should move the robot and not the trees or cloud. We can also generate various environments from first-person perspective. This is really important because that's how an embodied agent, like a robot, would perceive and interact with surroundings. So here are some examples of first-person view of a robot on a planet. This diversity, combined with first-person view, is critical for training agents that need to operate in both imagined and real-world-like scenarios. And the ability to generate consistent first-person perspectives in diverse environments also shows a strong grasp of 3D geometry and camera dynamics. We also see that the model has long horizon memory. It's capable of remembering parts of the world that are no longer in view, and then rendering them accurately when they become observable again. Genie 2 also excels at long video generation with new generated content. So unlike previous models that might loop or generate repetitive content, Genie 2 can introduce novel elements by maintaining coherence over extended sequences. It generates plausible content on the fly and maintains a consistent world for up to a minute. And we also see that one of the most powerful features is its ability to generate diverse environments, all the way from racing games to villages to more alien landscapes. This ability really provides the synthetic data necessary to achieve the scale of training required for general AI. And the diversity of these generated environments really shows a powerful underlying generative capacity that has learned to disentangle characters, content, and dynamic. And you can also interact with objects. So beyond just navigation, Genie 2 can also simulate various object interactions, such as bursting balloons, opening doors, and shooting barrels of explosives. And lastly, it also exhibits an emergent understanding of physics, including simulating phenomena like water effects, smoke effects. And the implicit learning of physics is crucial to simulate dynamic, real-world environments where physics laws govern these interactions. And it allows the world model to serve as a high-fidelity neural simulator for training agents. And the emergent understanding from video data implies that the world model is learning a compressed, generalizable physics engine just from video. So instead of being explicitly programmed into these physics rules, Genie 2 learns these rules implicitly by observing how the objects behave in videos. So that's a bit about our world models. How can we build agents with these amazing world models? So we can take a step back and look at how people trained agents in the past. So in the past, people focused a lot on control tasks, like teaching a cheetah to run, teaching a humanoid robot to walk, or teaching an ant to move forward. And this is all done through reinforcement learning, where we teach the agent to optimize some reward function, in this case, moving forward. And RL has achieved remarkable success in solving these control tasks from high-dimensional inputs, including these DeepMind control suite. So we typically train and evaluate RL agents in single environments, but RL agents overfit very easily to specific environments in which they were trained. So for example, if you train the cheetah in the environments on the left here, it does not even generalize to the environment on the right here. So this prompts an important question. Can we learn more general representations for these RL agents? So one approach to address this is domain adversarial reinforcement learning, which is the setup where we train on a distribution of environments, and at test time, we aim to zero-shot generalize to a new environment. So through domain adversarial RL, we want to learn a robust policy that can generalize to unseen environments. So how we did this was through this adversarial learning trick. So in DeepRL, we have an image encoder that encodes the frames to a feature Z. Then we have a critic network that tries to learn the Q value. We concatenate the feature Z and the actions being taken A and pass it to the critic network to learn the Q values. So what we add here additionally is a domain classifier, which, given the feature Z, tries to predict which domain the observation came from. But we want to learn features that are indistinguishable across domains. So we have this gradient reversal layer, which reverses the gradient when backpropagating through the encoder. So with the gradient reversal layer between the encoder feature and domain classifier, by directly minimizing the domain classification loss, we train the domain classifier to distinguish the domains from the state features, and simultaneously train the encoder to produce state features that maximizes the classification error, therefore encouraging invariant features that are indistinguishable across domains. And we train and minimize the critics loss and domain classification loss jointly. And we can do this through just one backpropagation pass because of the gradient reversal layer. And let's look at some results. So we compare against state-of-the-art RL algorithms such as soft actor critic and DRQ, where the training rewards are in solid lines and the test rewards are in dashed lines. And we see that with the baselines, they really have this big generalization gap between the train rewards and test rewards. Whereas in our methods, we have a much lower generalization gap. And thanks to this better generalization, it outperforms all the baselines on testing tasks. And the domain adversarial module really improves generalization to unseen environments, and in some cases also improves the reward on training environments, as it encourages efficient task representations. So these are all old school RL, where we train policies from scratch. We tweak these individual layers. So when LLMs came about, we were wondering if LLMs can act in interacting environments. So LLMs are remarkably general, and these capabilities usually come in two flavors. One is the ability to produce outputs of high quality from short and often underspecified prompts. And another is the ability to learn new patterns and imitate algorithms in context. This is what people call in-context learning. So we're wondering, can LLMs act as agents in interactive environments? So we took a bunch of these environments, like Atari games, chess, and these like Cheetah Run, Grid World, and we give these states to the LLM as input, and we ask the LLM to predict the next actions. And we try a bunch of different state representations, all the way from images to ASCII representations to also the coordinates. And it turns out, no, LLMs cannot directly act in interactive environments. So it's really funny because these LLMs have detailed knowledge of these domains when creating natural language. So for example, it knows what Atari games it's in, it knows a lot about different chess moves. But these declarative knowledge fails to translate into effective decision-making. And this is known as the knowing-doing gap that is observed in a lot of recent benchmarks like Bellrock, LMAct, and VGBench. So then we were wondering, okay, that's reasonable because these LLMs have never seen these agentic action data before. So what if we show these demonstrations in context? So we can take these expert demonstrations and we give it to the LLM as input in the prompt. So in the input, we have a preamble, and then we give it a bunch of demonstration episodes, like demonstration trajectories. And then in the current episode, we ask it to predict the next actions. Note that for some LLMs like Gemini, the context length is really long. It can scale up to millions of tokens, so we can actually put in a lot of demonstrations in the context. And it turns out with expert demonstrations, some models approach expert performance on simple tasks. All models beat random baselines, except on Atari, where the input is visual. I think this is consistent with people's findings that in-context learning with vision is quite difficult. We also saw that frontier LLMs rarely reach expert performance, despite we're optimizing the prompt formats separately for each model and task. So this benchmark is open sourced, allowing the community to further investigate how to unlock these capabilities. It also really highlights this knowing-doing gap. It shows that even with long contexts, direct LLMs are not sufficient for complex embodied tasks, suggesting that further training of these pre-trained models is needed. So how can we train these models further to become embodied agents? So given the challenges with LLMs directly acting in these environments, we explore building agents on top of these pre-trained models through SIMA, scaling instructable multi-world agent. So in LMAct, we saw that LLMs couldn't directly act, as it has never seen agentic data. So in SIMA, we collected large-scale keyboard and mouse data from many diverse domains. This rich multimodal data sets captures a lot of human interactions across various environments. And the use of large-scale keyboard and mouse data for behavior cloning is actually really practical and general, because unlike complex API-based integrations, keyboard and mouse inputs are a universal interface for anything. So if you have an AI that knows how to use keyboard and mouse on a computer, it can really just do anything on a computer. This also makes the data collection very scalable across anything humans can do on a computer. So this massive data set is then used to apply large-scale behavior cloning with pre-trained models to train Sima. The agent is given the language instructions, image of the current state, and it needs to output the keyboard and mouse actions. And the hypothesis is that by training an agent to a vast array of tasks and interactions across different worlds, it will learn more generalized and robust behaviors. So traditionally, RL agents specialize in one environments, leading to the brittleness we were just talking about earlier. And Sima's approach here really tries to learn generalizable behaviors across this wide spectrum. And we see that the trained agent is incredibly general and can follow language instructions and act in a variety of environments. We also see some nice properties from generalizing across domains. We see that the agent trained on many domains was better than an agent learned in that one. So if we train an agent across all the 9 domains we had at the time, it significantly outperforms an agent trained specifically for that domain. And what's more, an agent trained in all but one game performed nearly as well in that unseen game as an agent trained specifically for that one. So this leave one out setting almost match these environment specialized agent. This is very important because the ability to function in brand new environments really highlights Sima's ability to generalize beyond its training. So we then thought, what if we put Sima agents into the world model? This is really cool because the synergy between Sima agents and Genie-generated worlds is particularly compelling. Sima agents has never seen these Genie 2-generated worlds before, yet they can operate within them by following natural language instructions. So here you see that the Sima is controlling the person via keyboard and mouse inputs, while Genie 2 is generating the next frame and generating the 3D worlds. And we have more examples here showing Sima's versatility. So we can go to a more abstract setting of a knight with a sword. And we see that there are a bunch of doors, and we see only one with stairs behind them. And we see that the Sima agent has learned to follow language instructions in these completely simulated environments. We also have a few more examples where the Sima agent it's following language instructions to navigate to different places. And once again, this is all everything is entirely AI generated. The agent it's Sima generating the keyboard and mouse actions, and each frame is generated by Genie, basically generating the 3D interactive worlds. So bringing everything together, I think everything we talked about here really shows this path towards more general agents. So Genie 2 introduces a new paradigm of foundation world models, generating infinite 3D interactive worlds to build embodied agents. Many robotics companies are building world models now because neural simulators are very important in robotics. And LMAct extends large language models into interactive agents by grounding them in environments. These are also really, people are exploring this a lot. They call these the Vision Language Action Model, the VLAs. And in Sima, we're building language agents across 3D environments. And with these all coming together, we can really unlock self-improvement with infinite AI-generated environments, foundation model as agents, and algorithms to enable LLMs to improve in novel environments. And these developments set the stage for a new generation of agents capable of reasoning, acting, and self-improving across diverse domains, including real-world ones like computer use and robotics. And I'm very excited about that future. So that's the end of my talk. Happy to take questions, and feel free to reach out and connect. Thanks very much.
Oh, yeah.
Oh, yeah.
Yeah, again, great talk. Since you use synthetic data for training, how realistic is it to put these world models in the actual physical world in a robot and expect it to work? Is this primarily meant for simulated worlds, or would you feel that having more realistic training data rather than synthetic data would be needed to put the world model in the real world as such?
Yeah, that's a really good question. So people are already putting these world models in the real world. So a lot of the very big robotics startups or just robotics team in general, they're all building world models, basically neural simulators to simulate these trajectories for robots. That use case is very important because data collection in robots is just so expensive and you can simulate everything pretty accurately. And so people are already actively working on putting this world model into the real world in robotics. And
Thank you for that great talk. Miles Harrison from Practicai. You mentioned that SEMA was trained on large-scale keyboard and data. Can you comment on where that data came from?
We collected them. So we collected very large-scale keyboard and mouse data with human contractors. I think that's a pretty big area right now. There are a lot of people, a lot of companies collecting keyboard and mouse data because people want to build these computer use agents. And if you have keyboard and mouse data, you can really generalize to anything. So I think all the frontier AI labs are actively collecting these kind of keyboard and mouse data from human contractors, from professionals across different domains.
Yeah, thanks for the great talk. So how about the accuracy of the world model of simulator? Do you consider about simulation to reality gap? And you mentioned self-improvement. So how can we do self-improvement? Where's the data from, or reliable data, or even ground truth data?
So I think we saw some nice scaling loss properties with world models. So in general, the more data you train on, the better the model gets. And there is a lot of video games and also just video data in general. You can imagine basically training world models on all of the video data there is, which you can learn a very capable model. And when it comes to self-improvement, you can really have this data flywheel where you use the world model to generate synthetic data, and then you can train agentic models with these synthetic data, which generates more data, which you can put it back to the world model. So you can create this data flywheel that fosters self-improvement across time.
But synthetic data may not be the ground truth data, right?
Synthetic data is not ground
truth. May
truth.
not be the ground truth data.
You can also use the ground truth data. You can do a nice mix of synthetic data and ground truth data.
I hope this is not too much a silly question, but my kids watch a lot of YouTube videos to learn how to play video games. Do you think this technology can be used to create tutorials to learn how to play video games?
That's a good question. I think there are startups that are actively trying to build these video game agents and applying them into the game itself. I've seen a couple of startups that are doing basically building these AI where you can drop it into a video game and help you play video games or teach you how to do some things. So certainly, I see a lot of applications there.
I'm curious about how the memory is managed in the world model, because if I burst a balloon, how does it remember that the balloon was burst if I turn around and look at it?
That's a very good question. It's basically maintained through the context window. So the model has a very long context window, so you can remember events from the past. But that's definitely a very active area of research. I think there has been some people release some Minecraft world models, but for that one, it has very short context window. So you see that if you look at some object and if you turn around, and that object is no longer there because the context window is so short. Whereas for Genie 2, we really scaled up the context window, so you can remember things for a long horizon, extended amount of time. That's definitely an active area of research. You can definitely incorporate memories into these models as well.
Is it possible to impute objects in the context memory as of now?
Is it possible to what?
Impute, I want to, let's say, add an object dynamically in the context. So is it possible currently?
Add an object in the memory. I don't think currently it is not, but I think that's very doable in the next iteration.